the registration, and I think the video is really significant. I want just to draw your attention on a couple of clips in the video, because I think, as I said, that this is indeed significant. And so let me go back here. Let's see. Okay, so first, if you look at this clip, you see a perfect representation of a two-layer aquifer. The layers may be more than two, maybe 3, 4, 5. Like in this region, we have at least 3 layers. And you see what is the difference between the confined aquifer, which is the upper one, the unconfined, which is the upper one, and the confined, which is the lower one. And in the video, they said an important thing, 2 important things that I want to emphasize. First, the recharge of the confined, of the deep aquifer, is slower. And we discussed already the importance of flow to ensure sustainability. If the recharge is lower, you can understand the use is less sustainable, because it may take thousands of years to get the aquifer recharged. For the unconfined aquifer, which is closer to the surface, the recharge is faster. And this makes this resource extremely important for sustainability. But on the other hand, it is more exposed to pollution. And this is the second important thing that I want to emphasize. You see that the confined aquifer is recharged typically by higher elevations. So it doesn't get all of the recharge from the soil that is just above. It takes the recharge from soils that may be displaced very far from where we pump, and typically at higher elevations. You see here clearly the structure of the aquitard, which in a way it goes up in the mountains, and at a certain point it intersects the land surface. So basically this means that the confined aquifer, after the intersection on the left here, is directly recharged by infiltration, but very far away, which means that water takes a long path from infiltration to pumping, which makes the water protected, because the soil is like a filter. But still, we have to take into account that this confined aquifer has a recharge that is very slow, if it is recharged at all. This is another important thing that in the video they said. Maybe that the confined aquifer is like a bubble that was during tectonic movements was included within a kind of limited and a kind of megapore into rocks that are not permeable. So if you have this mega bubble that is isolated into a rock, you understand that it also may be the case that the recharge doesn't take place at all. And this is called fossil water, typically. It is very high quality because, of course, it is a water that is a long age, but on the other hand, the use is not sustainable. Understanding this displacement of aquifer and aquitards is extremely complicated, because you have to make local survey prospections, which means that you drill wells, you drill piezometers. Piezometers are just very small wells that you put into the deep soil in order to understand what is the level and pressure of the aquifer that you find there. And but you can make only a limited prospection, a limited surveys of this type. And therefore, understanding what's going on is really complicated. And what makes the confined aquifer under pressure? There was a small mistake in the video. They said it's the weight of the soil above. It's not really that builds the pressure. It's the column of water that is above the aquifer. So if you pump here where you have these, the position of my mouse, like they showed later, the confined aquifer is under pressure because you have this column of water on the left that is high above the position of the aquifer from which we pump. And this column of water has a weight, and it's the weight of water that puts the aquifer under pressure. It's not the weight of the soil. Okay, and also you see another important issue. In the confined aquifer, you have water that may spontaneously, once you put a piezometer or a well, the water may spontaneously drop out from the well. So no energy may be required to use water from the confined aquifer until it is in pressure, because it may be that after a while the pressure decreases because, of course, by using water, the height of the column of water goes down, and therefore you get less pressure. But it is also another nice feature, the fact that you don't require energy. And instead, for the, let's see, for the confined aquifer, for the unconfined aquifer, you see the effect of pumping. You have this depression cone, it's called the cone of depression, around the well, because you get water, and therefore the water level around the well goes down. And the cone quantifies the circle of influence, the circle of soil where you have a perturbation after pumping. And you see that in this case, if you lower down the level of the water, what is called the water table, in an unconfined aquifer, you have the water table level. If you lower it down, it may be that you drain water from the river, while without pumping, probably you have the aquifer feeding the river. So when we pump from aquifer, we may also cause a depletion of surface water because of the inversion of the flux. So these dynamics are, as I said, difficult to see. They cannot be seen, difficult to be monitored, and difficult to be modeled, because you understand that if you want to reproduce with the mathematical relationships these dynamics, it's not easy. You need information, and you are dealing with something that is really heterogeneous. The porous media are highly heterogeneous in the three directions, so the modeling is quite complicated. This is also why several students don't like groundwater modeling and like more surface water modeling, because it's something that can be seen and it's relatively easier to be understood and to model. But I would say that actually aquifers, for the very reason that are basically unknown, they are more fascinating, and they represent today a relevant challenge for us in terms of sustainability, because, as I said, there is a lot of countries that are mainly relying on groundwater for their water supply. And basically, we are relying on groundwater in a kind of blind way. We are using it, but we don't know if the use is sustainable. Okay, so let's try to get into more details then, so we can close this video. And you see that everything is basically reproduced in this figure, which is on Wikipedia, where you see also the effect of vegetation, and you see that there might be also some connection between the unconfined aquifer and the confined one. You see that there are some arrows that are directed perpendicularly to this layer of reduced permeability, because indeed aquithards may be layers with reduced but not zero permeability. So if you have a reduced permeability, it means that you may have some exchange of water between the confined and unconfined aquifer. And this exchange is extremely important. Furthermore, I just give you some ideas of how complicated the system is. In some regions, like the Emilia-Romagna regions, we have a lot of wells, and I would say that probably we have thousands of them. And if you look at a map, I have one, at a map of the wells that we know, which are whose existence is known, it's impressive. It looks like it is really, in Italian we say a punta spilli, which means that there are many wells distributed, thousands of them, and you have to take into account that some of them are not known because you know, sometimes people just independently, autonomously, without telling anything to anybody, they just dig a well, they make a well, and they use water. And as I said, we know that many of them, if not most of them, are not known. These wells, some of them have several filters, several windows. What does it mean, a window? It means that the well can take water from more than one aquifer. So typically, when we, for important wells, we put several windows, meaning that we take water from both the confined and unconfined aquifer. What does this mean? It means, on the one hand, that the well is more efficient, is more resilient. It may take water from several sources, but it means that when we take water from the well, we don't know from which aquifer we are taking it. So it is just, again, a trial and error. And the only way to monitor, in a way, is the water level. But the water level, given that the confined aquifer is under pressure, is not really an indication, the water level into the well, of the origin of the water. So it may be that the water level in the well is at the level of the unconfined aquifer, but the water comes from the confined one under pressure and goes up. And multi-windows means that we establish an artificial connection between aquifers, because the well is like a pipe with several holes, and therefore increases the permeability. Several holes, several windows, increases the permeability artificially. And we don't know to what extent this helps in recharging the unconfined aquifer. It's something that we simply don't model because we don't have enough information to understand how water exchanges travels between aquifers. Okay. I would say that what is the way to get information, to get data? What is the analog of measuring daily river flows? It's aquifer testing. Here there is a link, and let's see if I can. I already contributed to Wikipedia, so aquifer test is, or a pumping test, is a way to gain information. What do we do with an aquifer test? Basically, we go to a well and we pump a lot of water. We make a stress. We provoke a stress. And first, we measure the initial water level, and then we measure the volume of water that we pump out. So water level is 0. After pumping 100 cubic meters of water, the level is minus 10. So we measure the decrease of the level and compare it with the volume of water that we took. And this may give an estimate of the impact. You understand that if you take a lot of water and the level doesn't decrease, you may say, oh, the recharge is very quick. Or the aquifer is well extended, the recharge is not quick, but the impact anyway of my withdrawal, water withdrawal, is very limited because it looks like the aquifer is undisturbed. So this is a good sign. Another good sign is you pump, you get a decrease of the water level of 10 meters, you stop pumping and you measure the recovery time. If the water level recovers quickly, this is another good indication. It means that the aquifer is resilient. It can react to the shock. However, the process may be non-linear. So it may happen that you pump water, you don't see any impact. Suddenly, you pump a drop more, and the level goes down 10 meters. This means that the process is non-linear. I think that you know what is linearity, non-linearity, but just to make sure that you understand, and if you don't know what is a linear function, go to Wikipedia, linear function, and you get the definition, the mathematical definition. But I just want to tell you a couple of things. If a process is linear, you can apply the superimposition principle, which means, you know what it means, which means that if you apply two disturbances, the result of the two disturbances is equal to the sum of each single disturbance, which means that you avoid the fact that a single drop more brings you in a catastrophic situation. Okay, you avoid this. If the superimposition principle applies, it's impossible that you get to a threshold where a single drop more is causing a disaster. And let me give you a more practical example. Take a glass and you fill with a constant volume of water, constant rate of volume, constant flow, and you measure the relationship between the flow of water and the level in the glass. It's linear, okay? Because you see that the level increases constantly, and you can apply the superimposition principle, meaning that if I pour into the glass 2 volumes of water, the level in the glass that I obtain is equal to the sum of the 2 levels that I obtain by pouring each single volume. This is the superimposition principle. But when the glass gets full, then the superimposition principle doesn't apply anymore. This is a threshold. If you put a single drop more, you get a flood over the table. Okay? And this is an example of a nonlinear process. The process of filling a glass is linear up to the level of the glass top. Okay, and then I mean, this is I think a useful example. So even if you test an aquifer and you see that everything is under control, you cannot exclude that the process is nonlinear. And again, if you are not familiar with linearity, nonlinearity, please have a look at the definition. I assume that you know it, because for sustainability, nonlinearity is extremely important. Sustainability means be very concerned by thresholds. I want to show you one thing, one figure, which I found very interesting. Let me just see if I can get it quickly. I should go to OneDrive. And I'm not sure I can find it quickly here. Just give me 1 second. Otherwise, I will show you later. This computer is very slow. Okay. No, I cannot easily go to, just 1 second, let me check. Okay. I'm slowly getting it. Just 1 second. This is the one which I wanted to show you. Just 1 second. this may be too large. Let's see. Still too large, just 1 second. Maybe 100 is fine, less than that. 75, 50. Okay. This is the figure that I wanted to show you, and let me see, window size, still no, this is too slow. Window width, okay, very good. This is the figure that I wanted to show you. Let's refer to, with a sketch. This is a figure that I saw during a scientific presentation. I asked permission to the author to reproduce it. Basically, if you refer to a certain state of the Earth system, which may be state of water resources, groundwater level, you start from a situation which we define stationary, which means that it's unperturbed situation. And then you induce perturbations with up and downs, and you see that there is an increase of the state, the level of the state. We assume that this makes path towards a more critical situation. So the state, increasing level of the state means that you are getting to a more critical situation, and then you may get to a threshold. And when you get into a threshold, basically you get into something that is unknown. So while the stationary state and this state with the continuous blue line is something that we can monitor, that we can know, when we get to the threshold, we don't know what is the future evolution. And the future evolution may be a situation that goes back to normal. It may happen. It may be a situation that slowly gets to an unknown state that it's much different than normal, or quickly goes to this unknown state. And this is called, in this case, a tipping point. A tipping point is a threshold that, if it's crossed, leads to a new equilibrium of the system, a new stable equilibrium of the system, which is different. And a typical example is if you cut a forest. So if you cut just a few trees from a forest, then it's not a problem. Then the trees basically recover, new trees come up. If you cut a lot of trees beyond a certain threshold, you have brushes that may grow instead of the trees, new species. And these brushes may compete with the remaining trees and kill them. And therefore you get to a new state where you have brushes, you have savanna instead of a forest, for instance. This is something that we know. It's something that is very concerning for sustainability. I mean, the Earth system, certain states of the Earth system may have more than an equilibrium situation. In the case of aquifers, we have an equilibrium situation, which is the current one that we found. But there is another equilibrium situation where groundwater is dried up, and it's equilibrium because it may be that if you pass a certain threshold, then it takes 1,000 years in order to get back to the original equilibrium situation. The new equilibrium situation is something that is impossible to recover during the span of generations, of human generations. Of course, if you recover in geologic times, it's something that it's not sustainable. Okay. So we make these pumping tests, which allow to get some information, but still it is something that is it's not enough. So there are several unknowns which in a way are related to the use of groundwater. I just want to give you a final information about this. Today we have Earth observations, Earth monitoring through satellites that give an additional and very important opportunity. You know that we are observing the Earth from satellites, and there are a lot of satellites programs that are collecting more and more information that becomes every year more and more refined. Managing this information is extremely, it's demanding. We need the computing resources that are really important. And you may know that recently in Bologna, the European Center for Meteorological Forecasting installed a supercomputer. It's amazing, and if you get an opportunity to visit it, it's amazing because it's a big room with a lot of noise, a lot of fans, and a lot of computing units. It's something really massive, which are running in parallel. In parallel means that they are running all together to analyze this data, which are derived from satellite observations. And the amount of information that is collected is massive. They collect information on soil moisture, water level in big water bodies, so huge rivers and lakes. They collect state of the vegetation, so if the vegetation is green rather than different colors. They collect land use and several meteorologic variables. And the resolution is very fine. It's a kind of 10 kilometers resolution at present, which means that every 10 kilometers you have an observation. Of course, you have uncertainty, but it might be compensated by the huge amount of information that you have. And also the time resolution is very getting finer and finer. And it's not yet clear how this information can be used. Here I want to give you an example. They are also measuring the gravity forces, and gravity forces are related to the mass of the Earth. Where there is more mass concentrated, you have more gravity. And therefore, measuring gravity turned out to be a useful tool to measuring the amount of water that is stored into the ground. If you have a change in gravity, and you can exclude other reasons like volcanic eruptions or etc., changes in gravity can be given by depletion of groundwater resources. You know that water is very heavy, water has a huge mass and mass density, and therefore when we take groundwater we can observe the changes in gravity from satellites. And by using this technique, several scientific researches have been carried out in the past 20 years to understand what are the regions of the world where we run the risk of depleting groundwater. And we know today that in the Middle East, for instance, where there are a lot of groundwater resources that are massively used, indeed we observed a decrease of gravity. There is some uncertainty, but the message that I would like to convey to you is that we are expecting from the near future a revolution in Earth observation and use of Earth observations. And this will give a significant contribution to sustainability and management of water resources in particular. So, I mean, this is extremely interesting. I will tell you soon about the European Center for Weather Forecasting, because they asked also me to make you aware that they have some what they call student challenges, and they have some questions for students to be addressed. They are particularly related to weather forecasting or use of Earth observation data. And if the students elaborate ideas in order to use this data, they make this context, they identify winners, and they give also a financial contribution, which is something few thousand euros, but still it may be an opportunity. And keep in mind that in order to compete in these challenges, you have to be good in numerical computing, because to use these observations, there is no other choice than using GIS and making numerical computation, so computer programming. Most of these challenges are related to designing even simple computer programs to show that their data are useful. But I will provide you the information because I think it may be interesting. And also, yes, I get to your question. Also, I think everything that makes you connected with possible job opportunities is interesting, and not only job opportunities. I mean, also institutions. Institutions may be not really good for finding a job, but may be good to find connections. So if you get institutions like local administrations that in a way know that you have good skills, they can help you in getting connected to the job market. You had a question?
Yes, also you said that the change in gravity. Could you explain a little more?
Yes, the question is, can you explain more the change of gravity? So the gravity force is related to the mass of the body. So you know that every body basically may attract other body with a force that is proportional to the mass of the body. And the Earth has for instance, has a gravity force of a gravity acceleration of 9.81, which we call g. And if you go over Mars, Mars is smaller, and the gravity of Mars is 0.6 g, okay, because Mars is smaller. This gravity force is not constant for the Earth, because where you have concentration of mass, it's higher. And you can understand that, of course, because gravity is proportional to mass. And so where you have concentration, this gravity is higher. So keep in mind, gravity, we consider it as a constant. It's not constant. And if you move over the Earth, it's more or less constant, but there are small changes. And so if you deplete groundwater, you have a reduction of mass of a local reduction of mass of the Earth, and you have a reduction of G.
Professor, I ask you because I know that the axial force of the Earth is like this, and it's changed like this, and actually you know that the gravity to the North Pole and the South Pole is different. So it's related to the changing the axial force of the Earth, or
I don't know if there is also a relationship between gravity and the change of the inclination of the axis. I am sure that there is a relationship between local mass density of the Earth and gravity. And maybe also, I wouldn't say that it is related to the change of the inclination. I think that the change of gravity is related to the change in mass density, not in inclination of the axis. I don't think it is really, unless, no, I don't think so. I don't think it is related, but I'm not an expert, so you should try to get information from somebody else or the web. But for sure, it is proportional to mass density of the Earth, which is varying. And if you have, for instance, also rocks, they have a huge mass density and you expect a higher gravity. But in this case, you don't see changes. You get changes when you, in a way, decrease the mass density of the Earth's body. And of course, you cannot detect changes in a small aquifer. But for big aquifers, you need a good extension, because the pixel of the gravity measurement in the past, it was 25 kilometers. Now it's 10. But 25, you understand, if you have an aquifer with an extension that is more limited, you don't get it. And also, besides the size of the pixel, I mean, you need, in order to see a change on gravity, you need to see a huge change in mass density. And therefore, a small aquifer wouldn't make a big change.
Thank you.
Okay, I think I gave you a panorama of how aquifer works and a panorama of the inductive way of assessing their status, which is basically measuring water levels in wells. And we don't have a corresponding tool to the flow duration curve in order to estimate what is the amount of water resources that we can take from a well. The only thing we can draw is a relationship between water flow, withdrawn water flow, and water level. And this is the only thing that you may depict for a well, and this is the usual way that institutions use and water boards use in order to monitor their wells. They give you withdrawal flow and series of water level. Keep in mind that these measurements of water level, very recently, they have been automated, but in the past, they were not automatic. They measured them with a person going there and making a physical measurement of the water level into piezometers or wells. And this was done up to the year 2000 every 6 months. And then from the year 2000, I'm talking about Italy, you can find data that are collected like daily. That is to say that the water level usually in wells is less variable than water level in rivers because everything is slower in the aquifers. The flow is lower, the withdrawal is slower if compared to the volume of the water body. And therefore, one measurement every 6 months in the past was deemed to be enough because they were interested in monitoring the long-term changes. For a river, it wouldn't be enough, absolutely, and a measurement every 6 months. Conversely, for a well, the daily measurement is not really that useful. And usually, I say to the water boards that I need a measurement every week, and it's fine. Because if you see the variability is indeed very limited. Okay, but so far we talked about inductive assessment by looking at the data. And now I think we need to move a step forward because there is another way, as you know, to analyze a process, whatever it is, which is the deductive way, which means that inductive means that you look at the results and you try to go back to the process and understand from the outcome of the process how the process works. This is inductive, okay? Inductive is like I toss a coin and I measure the number of times I get an head, and I see that more or less it's 50% of the times. And then from the results of tossing a coin, I gain the intuition, the knowledge that I have the same probability of getting a tail or getting an head. This is inductive. But there is another reasoning that I can adopt in order to know, to inspect a process, which is the deductive. I start from the theory, I make a theoretical explanation, and this theoretical interpretation brings me an understanding. And then, if it's possible, I may verify with an experiment if the theory works well. And this is the deductive way. Tossing a coin, the deductive way is I look at the coin and I see, I think this is a balanced coin, so why should I expect a different probability of getting an head with respect to getting a tail? And therefore, I build a model based on my understanding, preliminary understanding, a theory, which says basically if the coin is balanced, I have the same probability, 50% of getting an head with respect to getting a tail. And this is deductive, because I start from a theoretical interpretation. And then I may make an experiment to verify if the theory is correct. Usually this is the way science works deductively. We make assumptions. Based on the assumptions, we construct a theory, and then we verify with experiments the correctness of theory and assumption. Sometimes we don't have the opportunity to verify, and the process may work anyway. It's still deductive. Okay, so the deductive approach implies in our field building a model, because we have to describe processes that are quite complicated. It's not just like tossing a coin, and very often we have to build a model. The model may be very simple or maybe more complicated, and it's typically a mathematical model. So let's turn to the next lecture, Deductive Methods. And again, we can refer to groundwater or surface water. Let me see, I think I have the PowerPoint, let me open it. So again, we can let's refer to surface water first. And what do we need then if we want to adopt a deductive approach? First of all, why do we decide to take a deductive approach? Typically when we don't have data. When we have data, we prefer the inductive approach in engineering. Okay, we prefer to rely on observations. Keep in mind that in science, it's not always like that. There are some fields of research and some train of thought that tend to promote the deductive approach anyway, because there is some confidence that uncertainty is reduced for the sake of gaining knowledge. Think of a situation where data observations are highly uncertain. You may prefer the theory. You may prefer the deductive approach. This is not the case usually in engineering. In engineering, we trust data for several reasons. So in engineering, usually we prefer to rely on observation of the process. And this is why Leonardo said, when dealing with water, just use first experience and then the theory. Because there is, when dealing with water, there is more uncertainty if you start from the theory. Usually the observations are better. So if we have observations, we prefer to use them. The flow duration curve estimated with river flow observation is definitely better than a flow duration curve estimated with a mathematical model, definitely. And keep in mind that as an engineer also, and this is what I try to explain to other type of scientists, I say, look, keep in mind that engineers have a responsibility for what they do, a legal responsibility, because usually engineers are asked to design, to make a design. And we have a legal responsibility for it. And we have to defend our responsibility if something goes wrong. You have to justify what we did if something goes wrong. And when you justify something in front of a judge of a court, you know, we have the question, is it easier to justify what I did with data or with an interpretation with a mathematical model? And this is something that I frequently discuss with my colleagues. I know a lot of scientists from different fields, and when I talk to meteorologists, they kind of understand. Because even for meteorologists, they have a responsibility. And the responsibility is clear. I make a prediction for tomorrow, it turns out to be completely wrong, and people may really experience damage or loss of lives. Think at meteorology, it's clear. There are several professions that rely on meteorological predictions, and they understand. But if we go, for instance, to speak with biogeoscientists or biologists working on long-term predictions, long-term strategy for recovering the environment, they have not so relevant responsibility as engineers or meteorologists. So this is something that I frequently discuss with them. And they say, look, we have a different perspective in engineering because we are responsible. And therefore, we feel really pressure. We really feel under pressure by several institutions who say, look, I want a prediction that I can trust. I want a reliable prediction. I don't want an interpretation of what's going on in the long term. I need a reliable prediction for something that I have the responsibility to make tomorrow. And this makes the perspective a little bit different. So the moral of the story is that usually we refer to deductive methods when we don't have enough data to support an inductive approach. Keep in mind that you have a gray zone. Usually we talk about data or lack of data, but there is a gray zone where you have few data. And sometimes you may be in doubt. When you are in doubt, my advice to you is use both approaches. When you feel that there is a risk, when you feel that there is uncertainty, the first rule is that you have to use the whole of the information available. You cannot neglect any kind of information when there is uncertainty. So you have to first have very clear what information is available. You have to use all of it. And the second rule of thumb, the second holy grail, is that if you can consider alternative solution, try all of them and compare the results. This is very easy. Sometimes one says, I have only few data, so I'm not sure this flow duration curve is fine. get a deductive method, estimate another flow duration curve, and then compare the two. If you see that they are similar, great. It means that I am fine. If you see that different methods give you different results, then it means that there is a lot of uncertainty, and then you have to be very careful. And then you may take the more conservative one, an average. It depends on cost-benefit assessment, risk assessment, extremely important. Okay, so surface water. Surface water, it's modeled rivers with a big branch of science of hydrology and water resources management, which is rainfall runoff modeling. Why rainfall runoff modeling? Because if we don't have river flow data, we may have rainfall data. And rainfall is the engine of everything. And for rivers, there is, for surface water, there is a very direct connection between rainfall and water resources. For groundwater, the connection is a bit weaker because the groundwater may be fed by rain that rained 1,000 years ago. And therefore, yes, it's rain, but still it's weaker. And this is something that I find hard to explain to water board managers. They say it's impossible that you can get an estimate of groundwater starting from rainfall. And my reply is, I don't know the rainfall of 1,000 years ago. And so it's really a connection that is weaker. But for surface water, the connection is very close. And therefore, it is perfectly logical that we start from rainfall and we try to reconstruct river flow. And this is why this branch of hydrology water resources management is so popular. What is a rainfall runoff model? It's a model, let me see, that describes a portion of the water cycle. This is a very classical figure of the USGS, United States Geological Survey. Keep in mind that what you find in governmental agencies of United States, it's public domain. And they are a source of figures, information, which is very relevant. And when you have to prepare reports, thesis, it is extremely relevant that you know what are, I already mentioned to you this problem, what is the information that you can freely reuse. And, you know, getting figures for the thesis is an important need. And try to get experience also on this complicated environment, which is the public domain. Okay, there are Wikipedia, public domain, Wikimedia Commons, keep in mind, for figures, pictures, is extremely valuable, public domain, and also the United States governmental agencies. So this is the water cycle. We know there is everything here. It's, there is groundwater, there is surface water. Rainfall runoff modeling tries to reproduce part of it. How to reproduce part of it? With a numerical model. You could reproduce part of it also with a physical model, a small-scale model in the lab. Some people do that, not for hydrology. Or, let's say, for hydraulics, they do that. Not for hydrology, typically, because hydraulics refer to a single river, refers to a single harbor, for instance, and these processes can be reproduced into the lab. Hydrology is difficult because it refers to large scales, and reproduce it in the lab, it's complicated. But for instance, geomorphologists, they do that. In order to study the shapes of the Earth, how the Earth was carved by rainfall, they do that. They use lab experiments. For us, to study water circulation in a lab at large scale, it's not possible. Because keep in mind, when you make a small-scale model, you cannot reduce much. You have a limitation on the reduction of scales. So you cannot reproduce a watershed in a scale of 1/100,000. And you want to reproduce water circulation in it. It's impossible. And you understand why? Because viscosity, when you reduce the scale a lot, becomes too large. You cannot reproduce the flow of a river in a scale of 1/1,000 because the water becomes very viscous at a small scale and you cannot reproduce it. This is why we cannot go into the lab and make a small-scale experiment for a big river. We can do it for a small portion of it, for a small river reach, for a short river reach, but not for a long one. So we cannot make lab experiments on rain for runoff modeling. We can only refer to the plot scale. Some people do that for plot scale, for studying very local phenomena, but not at the catchment scale. And therefore, we refer to a numerical model in order to make an experiment. And as I said, a limited portion of it, rain for runoff modeling, refers usually to surface water only. So in a way, we estimate infiltration, but it's lost. We don't want to model, we don't model with the same model surface water and groundwater because the processes are different. And we need to keep the model simple. Today, with the increasing amount of Earth observation, Earth information, and computing resources, there are indeed people, especially in climate science, that try to reproduce within a single model everything, starting from climate and then hydrology, groundwater, surface water. They try to reproduce everything. But if you put everything together in a single model, your scale of representation is very coarse, and you cannot reproduce very local processes. So when you know about models of everything, just wonder what is the scale of representation and spatial and temporal scale, and try to understand whether they give a useful information to you. Usually the engineer needs a very local information. I have to design a bridge here, not at the scale of 10 kilometers. And therefore I need a very detailed model of what happens here. And for this reason, we try to split the water cycle in pieces and model individually each piece. This is why we separate groundwater from surface water. This is why we have different models. Why do we want to reduce complexity? Because we want reliability. Complexity, keep in mind, means uncertainty. The engineer doesn't want to avoid uncertainty. The engineer knows that there is uncertainty in everything we do, but the engineer wants to reduce it and wants to estimate it. Uncertainty is not a problem if you know it. You don't risk if you know uncertainty and you have a good estimate of uncertainty. If you know that the timetable of the bus is precise with a precision of plus minus 5 minutes, you don't miss the bus and you don't wait a long time at the bus stop. But if you only know that it's uncertain, but you don't know if it's plus minus 2 or plus minus 30, of course you run the risk of missing the bus or waiting half an hour at the bus stop. So, I mean, you don't have to be concerned by uncertainty. It's fine. I mean, it's normal. The engineer cannot avoid it, but we want to estimate it reliably and possibly reduce it at most. Because if I reduce it, my design is more efficient. If I have a good estimate of uncertainty, I can mitigate the risk. If it is very large uncertainty, I oversize my design and I can mitigate the risk. But if I want to optimize my design, I need to reduce uncertainty. And therefore, if reducing uncertainty, I know that simplifying a model is reducing uncertainty, I want a simple model. And keep in mind, sometimes when we use simple models, we are in a way suspected that we want to avoid complexity because we don't know how to deal with it. In most of the cases, this is not the case. We have to make clear to our customers that we want to reduce complexity, not because we don't know how to deal with it, but because we know that complexity means uncertainty. And this is quite clear. I mean, if you have a task to perform and the task is very simple, you are confident that you will succeed. If the task is very complicated, then you start thinking, oh, I can make this wrong, this wrong, this wrong. There is uncertainty because, you know, uncertainty increases. So you're getting not so sure of if you will fail or will succeed. Okay, I go back. Now, what is the purpose of a model? I mean, sometimes we are concerned by the term mathematical modeling. Actually, it is a very simple concept. What is the purpose of a model? It is to reproduce some variables of interest. In this case, what do I want to reproduce? The river flow. Fine. The variables of interest, if I want to reproduce the river flow, may be more than one, because I may need to represent additional variables, like, for instance, storage. It's a time-dependent variable like river flow. And if you think of a tank from which you are pouring water, and you want to estimate the flow that you can get when you open the tap, the flow depends on the storage in the tank. If you have in the tank a huge storage, you have a good flow from the tap at the bottom. If the storage is reduced, you have a low flow. And this very simple example brings you to understand that even in a catchment, if you want to estimate the river flow, you need to also estimate the storage in the catchment, the water stored into this tank, which is called catchment. The catchment is like a tank. You know what is a catchment? You don't know what is a catchment. Okay, so I thought I defined it, but maybe I forgot. So it's a very good thing that you said no. And when we have a river, and a given river cross-section, I'm sure I already mentioned this concept, we need to know the portion of land that contributes to the river flow, that is collecting rainfall and bringing rainfall to that river cross-section. And this portion of land is called catchment. So what is a catchment? This may be a question at the exam. What is a catchment? It's the portion of land which only contributes to the formation of river flow to a given cross-river section. And I repeat, it's the portion of land that only contributes, you have to say only contributes to the formation of the river flow in a given cross-river section. How it is contributing? By collecting rainfall. A catchment has an area, it's a portion of land. Is it clear? Okay, it's like if you put a tank outside collecting rainfall, what is the portion of land contributing? It's the area of the tank projected over the horizontal plane. And for the same thing for a catchment. Let me just see if I have an example. I'm sorry, now I am using a page in Italian. What you can see here in let's say it's light brown, it's the catchment of the Po River. And you see that it's including a large area in the north of Italy. You see, it's light brown, and it's the contour is identified by brown line, and which becomes yellow in some parts. And it's brown where it's identifying a border, a country border. It's yellow when it identifies when it's not coinciding with the country border. And how do we identify the catchment? by following the divide. This is the usual way. The divide is what divides two catchments, and typically is a ridge, is a mountain ridge. When there are mountains, it's easy to identify the divide because it's mountain ridges. And in a plain, in a flat area, the divide is more difficult to identify. It follows ridges, but these ridges are very smooth, very flat, okay? And sometimes the divide is also dictated by artificial intervention, because sometimes we organize the drainage of the land with artificial channels. Typically in flat areas, we do that. And so this is the catchment, which in English is, in UK English, is sometimes called watershed. And it's also called the river basin. Okay, so just learn what is a catchment. And I think in some of my web pages there is a definition. I think in rainfall runoff modeling there is a definition. Let me check, because I thought it was there. Let me see. I think it is here. Let me see. Let me search for the word catchment. Okay. There is here an instance of catchment. So let me see if there is another one. Okay, the catchment is defined as the portion of land whose runoff uniquely, I said only, contributes to the river flow at its closure river cross-section. It's also called the closure. The closure of the catchment is the river cross-section, which I used to identify the catchment itself. Let me see if there is a definition also of concentration time. Yes, but later on. Okay, I go back to the PowerPoint. I was saying that if I want to estimate the river flow, which is my desired variable, I may need to estimate other variables which are necessary. And storage is a good example. Storage into the catchment. Now you understand what I mean. And this storage is time dependent, is an additional variable, and we call these additional variables, besides the output variables, we have the output variables. If we have additional variables, we call them state variables, because they basically describe the state of the system. The storage describes the state of the catchment. Sometimes this is a difference that is very subtle, and the concept that I want to, the difference between output variables and state variables, the difference is very subtle. The concept that I want to deliver is that we have to identify the unknowns, and these unknowns are our output variables, but maybe additional ones that we need to describe, which are the state variables. And sometimes we are also interested in the state variables like storage as output variables. So the difference is subtle, but what I want to emphasize is that we have to identify the number of variables that we have to describe. And then these are our unknowns. We need equations. We studied maths. We know that to describe two unknowns, we need two equations. If we have 2 degrees of freedom in the system, we need 2 equations. And therefore, this equation, I call it you can call them the constitutive laws of a model, or the constitutive relationship of a model. We need equation. And therefore, the first question is, how many variables do I have to describe? And the second question is, what kind of equations of relationship, of laws, should I use? And then once that you have the number of equations that is equivalent to the number of unknowns, you put the equation into a system and you solve it. Now, a couple of things. I have 5 minutes to go. A couple of things. First, what kind of equation? This was my question. What I am describing here, I am describing water flow. In water resources management, everything can be reduced to describing a water flow, which can be also water storage, because this is the flow as velocity 0, it becomes a storage. But in general, what I have to describe is the movement of a fluid. And what is the science that describes the movement of fluids, the movement of bodies? It's physics. So I have to refer to the laws of physics, which typically, and also keep in mind that in fluid mechanics, we can apply Newton laws. You know the 3 laws of Newton, and the force is the third. The force is equivalent to the mass for acceleration. I don't remember if it is the third or the second. So the force is given by the product of mass plus acceleration, and then a body stays in its state unless there is a perturbation, and any action corresponds to a reaction which is equivalent with the opposite direction or sign. And these laws imply conservation of mass, conservation of energy, and conservation of momentum. So these are the laws that I have to apply. Conservation of energy and momentum are closely related. And momentum is a vector, energy is a scalar, mass is a scalar. So these are the laws that I have to apply here. With conservation of mass, conservation of energy, conservation of momentum, you resolve any problem I wouldn't say any problem, but let's say the physical problems of hydrology, of the water cycle. And then there might be additional laws, thermodynamics law, biologic, ecologic laws, chemical laws, because if chemical reactions are involved, you need additional laws. But for what concerns the movement, and I would say, yes, the description of the velocity vector, the movement of water, you can describe them with the conservation of mass, energy, and momentum. I would say conservation of mass and momentum. That's it. And then energy, conservation of energy is a consequence of the conservation of momentum. These are the questions that you have to consider, which are very simple to apply. Conservation of mass is very simple. We will see examples. And second consideration, these equations need to be flexible because they have to be applied, they have to lend themselves to the application to different contexts, different possible interpretations. And how do we make a law flexible? Through parameters. Think at the conservation of energy. You have to quantify energy losses, the friction of water against the riverbed. And let's adopt a parametric relationship. Parameter means that, for instance, if I decide that a relationship is linear, we know the type of relationship. If I draw it on a graph, it is a rectilinear relationship. It's a rectilinear line. But I can change through parameters the slope and the location. If in the equation of a rectilinear relationship, I change the intersect and the slope, I keep the rectilinear shape, but I change, again, slope and location, which means that I introduced flexibility through 2 parameters. Instead of fixing the slope, I accept that the slope can be varied. Instead of fixing the interception, I allow the interceptions to be changed. These are parameters. I define parameters in a relationship as degrees of freedom that don't change the shape, the form, the concept of the relationship, but give flexibility in some of the behavior of this shape. So basically, I keep the rectilinear form, the linear form, I keep the rectilinear shape, but I give flexibility in the slope in those features that I can change while keeping the rectilinear shape. So the slope and the location. Parameters are usually constant. So once that you decided what is the best value for a parameter, you keep it constant in a relationship. So if I introduce a parameter to quantify friction, once I introduced it for a specific case, for a specific case study, I keep it constant. But there are also models that take time-varying parameters. I think I set the basis, and the bases are, let's identify our unknowns, let's identify what is the nature of the relationship, and let's adopt a parametric relationship. Then I just have to move a minor step forward, referring to some specific cases, reinforcement of modeling, and let's try to make some examples of models in order to describe their knowns. Keep in mind that when you identify the state variables, you may simplify things. So you may recognize, for instance, that temperature is important in reinforcement of modeling because temperature is influencing the viscosity of water. On the other hand, you may decide that this kind of state variable, you ignore it for the sake of simplicity, which means that you don't describe temperature, you reduce one equation, you get to a model that is simplified and less uncertain. Okay, I think today is Thursday. I would say that next week, I would prefer next week we have lectures in both days because the week later is degree day. I don't think we have lectures on Monday, but the next week we have lectures in both days, correct? And I would say that on Monday I am lecturing, and on Thursday we take the exercise. We make exercises. Just let me check if next week we have. Yes, you have both days of lectures. Okay, do you have any question? Okay, thank you very much. Let's have a nice weekend. While I am closing the recording, we can say goodbye.